Introduction to Image Video Processing, so OpenCV. Okay, and after that, we'll be ending with the day. So it's the last workshop of today. And essentially, this workshop will be about image processing, which is very important because it will enhance and extract key features from images and also prepare them to be used in computer vision. So this workshop will introduce you to I/O operations. So let's say read, show, write, basic image operations, mathematical and logical operations, image enhancement, filters, feature detection, and image segmentation. Well, another mouthful. You guys are too smart to understand all these things in AI. So, well, let Tim introduce Pravish, which we met actually last week for this first but not the least workshop of today.
Yeah, great. So very lucky to have Pravish give a workshop again this week. And Pravish Sainath is a co-founder at AI Launch Lab. So, been with us for years, and he's the Learning and AI project lead. He's a PhD student at Mila / Université de Montréal in brain-inspired AI and machine learning for neuroimaging. Previously at Hammerhead, which is a New York City tech startup, he was building software for bike computers. So thanks so much, Pravish.
Thanks a lot, Tim, for the introduction. I'm just going to share my screen. So today we're going to focus mainly on computer vision. So this is just a brief, very brief overview of computer vision, and then we'll transition into OpenCV, and we're gonna do hands-on some vision experiments to understand the basic concepts. Just as a warning, computer vision is a super huge topic in computer science, and it's actually 1 or 2 graduate level courses, the amount of content. But in terms of understanding it as new learners, we can try to get an overview of the basics and try to learn things which are relevant to the projects that we're working on, or get started with some basic project and learn these things on the go. So we're just going to very briefly touch upon these ideas about what is computer vision and why is it challenging, and then a basic pipeline for computer vision, and then we're going to look at the concept of color spaces in images, and some basic image operations and image transformations. Okay, what is computer vision? So the great philosopher Aristotle is believed to have written that vision is the act of knowing what is where by looking. Or maybe he did not say that, but vision is that. So given some visual stimulus or some data which is visual, we need to know what constitutes the visual stimulus, and where are these parts located, and have some meaning of what we see. And that's how we perceive visual input as humans. So when we talk about computer vision, it is the act of really helping computers to perform this task of vision. So it's a field of study by itself, and we need to do a lot. We need to do a lot of programming and design algorithms to help computers see and understand images. we will stick to the notion of images because visual information is essentially in the form of images, and from a computer's perspective, if it's like a continuously changing visual information like a video, it is still a sequence of images. So we will stick to the notion of images. And some examples of computer vision that is already happening. I don't need to introduce most of these. It has become mainstream over these years, or these past years, like optical character recognition, face detection, which most of us are using to unlock our phones and computers, biometric authentication, which some of us use at the workplace, and also commonly used with the phones and computers, and object recognition in factories to detect failures or like quality control and certain specific types of objects, and medical image diagnosis. Of course, doctors take a look at our scans, but increasingly we're having computers examine medical images and diagnose about specific medical conditions. So why is computer vision challenging? So the basic idea behind why it's challenging is there are many factors, but the most fundamental idea is called this semantic gap. Because when we look at an image, say an image of a cat like this, we as humans, we perceive, okay, okay, these are the eyes. Okay, these are the ears. I've seen cats like, we introduced to the concept of cats when we were young by either like seeing them in our neighborhood or in our homes, or in other sources, being introduced by our parents or teachers. And we've consistently built a notion of these semantic concepts, or like these meaningful visual concepts. And based on our experience, it's easy for us to detect that, okay, given an image, this is a cat. But this is challenging for a computer. And also, even if this is not a cat and like a very weird animal, we can associate that with like at least an animal, or even like, okay, a cat-like animal, because of our previous experience and our ability to detect these features. Like, okay, it has got the mustache, the eyes are definitely cat-like, so, and the patterns of fur or the skin. These are some semantic ideas, meaning which we as humans are capable of, but the computers don't really have this notion by default. So the semantic gap is about really the fact that we interpret these images in the terms that I just described, like eyes, nose, ears, and like, okay, it's got a body and so many other, like, for example, in this case, the environment, we have a notion of what is the main focus of the image, what is in the background, what needs to be ignored, what needs to be considered. But the computers, all they really see is a bunch of numbers when you feed images. Even if like you have a webcam, you have different technologies to capture images, all that the computers know is it could be the image of the most beautiful sight in the universe, yet for the computers, it's just a bunch of numbers. Specifically, it's like a matrix. It's arranged because images are two-dimensional. There could be three-dimensional images as well, with like modern technologies to record three-dimensional visual data with the help of LiDAR and other depth camera technologies. But in most common cases, an image is a two-dimensional arrangement of these intensities, which represent colors, which we call them as pixels. And for the computer, these are just matrices or two-dimensional arrays of pixel values. But for humans, and maybe perhaps other animals, it's more meaningful than that. So this is the semantic gap, which is a very fundamental challenge of computer vision. But apart from the semantic gap, there are other challenges which could prove difficult for computers to understand. One is called the viewpoint change. Even for us as humans, right? Like, you know, this example of the elephant at different angles. They look different for different people who have challenges seeing. So, like the metaphorical elephant, but like in practical terms, we ourselves have difficulties, right? For when we solve these captchas, especially these days, they're becoming more and more challenging because the bots are able to do this computer vision better and better. So they really test the human being and maybe test our abilities in intense moments. So viewpoint change is a challenge because the objects that you're looking at look different from different viewpoints. And then there's this challenge of illumination. In different lighting conditions, objects look different. And sometimes it really hides a good part of the image for really detecting what it is and some meaningful information from it. So illumination is another challenge. Deformation is what we expect objects to be is not the same all the time. For example, this is a cat and this is like having a nice sleep in the warm sun, and it's going to be hard to detect that it's a cat in this kind of posture, and which is not very common, perhaps like depending on your data set and stuff. And all the next one is occlusion. Maybe looking for the remote on the couch. When things are hidden, occluded because of the presence of other objects. And so here this is actually a cat whose tail is here, I guess. So occlusion, and then there's this clutter, the background and the foreground, like the actual cat is here and the background is almost in the same color as the cat. So it's hard for us to really spot as humans. So for computers, it's going to be even more challenging. And then there's this other aspect of intra-class variation. If we want to build the ultimate cat detector as our CV project, not all cats are the same. So there's this class variation even among cats. There's a huge number of types of cats. So these are like a lot of these challenges in computer vision. So now let's transition into the coding part. But for that, like I just introduced that images are matrices or two-dimensional arrays of numerical values. So what are these numerical values and how can we represent images? What do these cameras really capture? So this is based on the concept of color spaces. There are many different color spaces that you can use. Of course, we would have seen images which are in black and white, grayscale, and like color images. So black and white images are like these two-dimensional arrays, but they can hold only two values, like 0 and 1, or 0 and 255, or like any two values, just to detect what is black and white. And as you know, this was the dominant imaging technology like many decades back. And then grayscale is in this matrix, you can represent shades of gray, like white, black, and shades of gray in between them. So 0 corresponds to white or black, depending on the notion that you use. But let's just say 0 is black. let's just assume these pixel intensities to really represent the magnitude of how bright a pixel is. So 0 is like the absolute dark pixel. So 0 is black, and 255 is white, 255. So there are 0 to 255, there are 256 values that you can represent. So from 1 to 254, in between them, these would be shades of gray like these, right? So in this example, you can see here, this is a satellite image, a grayscale satellite image, and this is like a small patch. This is called a patch. Patch is just a collection of pixels, and each pixel here corresponds to a value between 0 and 255. So what is 255? Is that a magic number? No. The concept here is that we need to represent images using like on computers, and when we use binary notation, like computers store images in like binary, right? So these are just if these are powers of 2, it's easier for us to really encode these pixels in binary. That's the whole idea, and we completely use the number of bits there. So black and white and grayscale we just saw, and RGB is the most commonly used format, the color space, to represent color images. This, of course, I don't need to talk a lot about it in our art courses during our kindergarten, and about we would have seen that like on the boxes of the paints also, we would have seen the color wheel, which consists of R, G, and B, and D. It can essentially represent all colors by combinations of reds, greens, and blues. So whatever we saw for grayscale, we just expanded by 3. And red has 256 possible values, green has 256 possible values, and blue has 256 possible values. And the intensities combine to form a color image patch like these, okay? So just guess how many bits are required for these intensity values. Here in 255, the number of bits required is 8 for each pixel. So in this case, it just expands by 3. So that is about RGB. And these are other color spaces, which might be useful in certain applications, but let's just stick to RGB for now, okay? So the pipeline for any computer vision task really is simple, irrespective of whether you use machine learning or not. The idea of computer vision in terms of understanding what is represented in an image is very simple. I mean, the conception is very simple, but doing it is hard. If this is the input image, you need to apply some kind of pre-processing, like some geometric transformations to really highlight because as we saw in the examples, what you really want to detect or what you really want to understand might just be a part of the image and not the entire image. There could be a lot of noise, there could be a lot of background clutter, and so many other features which are not your focus. So you need to do some kind of pre-processing to, and of course, these days we use the filters in our cameras and in all these social media platforms. These image transformation methods have really redefined the notion of what is beauty and what is attractive, right? These days, so you would have yourself seen some filters which highlight certain features, certain parts of your scene. So once you do this pre-processing, you need to detect these features, some specific features of the image, of the part of the image which you need to focus on to really see what they are. For example, in this case, you can see the wheels and understand, okay, it's some category of vehicles, and you can see certain parts and figure out, okay, they're just 2 wheels and it's a 2-wheeler This has got to be a motorbike. This is not a bicycle because it has got like a different kind of a body here. So these are some features that we want the computer to detect, and then combine these features to really infer something about the image and make some predictions about whether it's a car or a motorcycle or a dog or whatever it is. So this is about what we're going to do. So we're going to look at some basic ideas from code to understand preprocessing, and we'll do some very basic feature extraction today, object detection, feature detection today. And next week, we'll see more details about how it can be done. So I'll see in the chat if there are quick questions. I'm going to start this is the example, this is the collab that we'll be working on. So you can open it up if you're in the mood. I know it's a Saturday evening, and if you're in the mood for coding, you can open it up, but I'm just going to look at some questions in the meantime. Oops. Okay. 3 Musketeers. Okay. Okay, there's just one question then from Simon. Do you absolutely need CNN in computer vision? Okay, that's a good question. CNN is a deep network to like do computer vision. We'll see it probably next week, but we don't absolutely need it, but increasingly, because of the semantic gap that I talked to you about, and like you cannot describe all categories of objects in concrete terms for the computer to understand. So CNNs seem to have proven to be like a good model to rely on. If you have a sufficiently large data set, they seem to be doing basic object detection and many other computer vision tasks sufficiently. So yeah, you don't absolutely need them, but in most cases these days, at least, if you really want to have some good results, maybe you have to use CNNs. Or if not, you need to discover some algorithm which is not CNN that does better than CNN. So it's on a case-to-case basis, just as a summary. Okay, so OpenCV is just a library which has been traditionally used to perform computer vision. CV here stands for computer vision, and open because it's open source. So this is a library of functions which it was initially programmed for real-time computer vision, meaning that you use the camera of your phone, and in real time it detects your smile, it detects the faces, and it's in real time. It does not capture the images and then do the post processing kind of. So it was initially conceived and programmed to do real time computer vision, but you can it was originally developed by Intel, but it was later supported by Willow Garage, and then now there are a couple of developers who are taking care of it in the community. But OpenCV is not the only way to do computer vision. There are other libraries such as scikit-image, but the concepts that we will see are going to remain the same no matter which library that you use. There's also one more called PIL library, which is also commonly used. You can use any of these libraries if you're comfortable, but it's only the syntax and how it's structured that's going to change. But the basic ideas are just going to be the same. We will see OpenCV here, but scikit-image is another useful tool. So this is how you install OpenCV in Python. OpenCV was mostly used in the C language, but we will use in Python because it's simpler and it's useful for many of our machine learning pipelines. So OpenCV Python is already installed on the Google Colab environment. And scikit image real time. Yeah, I think in a good number of cases we can use scikit image for real time analysis as well. The only bottleneck in terms of real time implementations is how fast it is, because when you use like for real time, like for a robot's visual periphery or something, because it keeps moving and things keep changing fast, you want the algorithms to run really fast so that it makes sense when you detect something. Otherwise, it's going to change by the time you detect. So it's about the speed, the agility. Because OpenCV is underneath, and the underlying library is implemented in C. It's pretty fast. Scikit-learn also has a good number of methods which are implemented in C with a Python wrapper on it. So some of them are fast, but maybe I haven't really seen benchmarks of if it's on par with OpenCV, but that's something that you can try when you're using your applications. So we will do some imports here. I'm not going to talk about these imports. I think time is running. So the main thing we will be looking at is this. Actually, this shouldn't be here. So import CV2. See, this is just the version of OpenCV, and CV2 is going to be we're going to bank on CV2 anything to do these image processing operations. And these widgets and other things are just for the purpose of demo you can play with. So let's just print out the version of the OpenCV that we're using here. It's 4.1.2. I think there is a more recent version, but this is what the Google Colab environment supports. And this is the Python version and all that. So we're going to clone a library just to download some sample images, which we're going to work on. So this is, you can refer to this library for more tutorials on OpenCV. They're really good. So you can see here, once you do this git clone, you'll have a folder. If you click on the directory icon on your left tab, you will see the sample imgs, sample images, and you will see a lot of images here. Like this is an example of an image. These are coins from India. This is an image. This is some factory steel thing. Yeah, these are Uno cards. So these are images that we're going to work on. These are like of different formats, if you notice, right? This get CWD just gets all the files in the directory. So like you have JPG image, like JPEG images, TIFF, JPEG, and so many other. You also have GIF images. You have so many formats of images that we downloaded. But let's see. So the first part we're gonna deal with. Like the I/O operations. Like now that we have some images, how do we read the image? How do we display the images? And how do we like input the images? So just as a summary, black and white images are also called binary images. These are 2D arrays of pixels where the pixels are either 0 or 255. Grayscale, they're integer values between 0 and 255. And RGB, they are like three-dimensional tensors. They have like 3 dimensions. They have a row, they have a column, and then there's one more axis called the channel. This terminology is very important when you work with images. That channel, it can be an R channel, G, or a B. It can be a red, green, or a blue channel. And each of these, so it's like a sandwich basically. If you assume like a 2-dimensional array to be a piece of to be a slice of bread, then RGB is just like 3 pieces of bread stacked one over the other. So that is what this is going to be. So CV2.ImRead is going to be the function. I'm not going to spend too much time on explaining every part of the syntax, but I'll tell you the basics. Okay. So CV2.ImRead. ImRead is the function. ImRead, right? Image read. And a lot of these names might sound a little bit different because these are based on the same methods that we use in the C language when we use OpenCV. So for those who have had some experience in OpenCV in C, this might be familiar. For others, you just need to relate these names with what they do. That's it. And also, as I said, you can always refer to the documentation. You can always Google the same name, and it's going to give you what it does. Okay, so this is an example of a binary image and an RGB image and grayscale image. We're going to pick from the sample images that we downloaded. But the most important thing is we need to tell OpenCV what type of image it is so that it infers the values accordingly. For example, because you can still read like a color image can still have just shades of gray, and a grayscale image can still have just black and white and no gray shades. So it's important that we really and if it's possible to even convert them. Okay, here you can see CV2.ImRead, and we're going to name the path of the image, and then this is called the flag. Flag is just an extra parameter that you pass, extra argument that you pass to a function to inform OpenCV about the image and something extra to be done. So ImRead unchanged means you read the format of the images as it is. If it's a color image, use them as color image. If it's a grayscale, use it as grayscale. Whatever is the raw value, which is encoded in the image file, we're just going to use it. Okay, and it's important that can you see here that we used BGR instead of RGB? So there is this thing in OpenCV that it does not use the RGB format, but rather uses BGR format for representing the images. This is simply the same thing reversed. Like we have some languages where we write from left to right, and others where we write from right to left. This is just a matter of convention, and this is more of a legacy format from when OpenCV was developed. So it's more of a convention, and it's nothing special. But we need to just be careful to interpret these values as BGR and not RGB when we do our processing. Okay, so we read the images into these variables, and we can use these variables. Let's just print the type of the image, the shape or size. Like shape is just the structure, and we're going to print these images one after the other. So if I run the cell, you can see that this is the RGB image, right? And this is the grayscale image. This is the binary image. The binary image here, instead of black and white, it represents in this purple and yellow format. That's just how matplot live, that we use to plot functions, but you can also change it. So the data type of the class is called numpy.ndArray. This is the NumPy library in Python. These are like faster arrays than the lists that we did last week. And the shape and size of the RGB image is 625 and 960 and 3. So you can see here, they're like 960. The width of the RGB image is 960. The height is 625. You can see it's a little more than 600 here. And the 3, as I told you, is like the third dimension, which is like the stacking of the R and the G and the B images together, which are superposed to produce these rich colors. And this is the grayscale image, which you see, as you see, the dimension is 512 times 512. So it's a little more than 500 and 500 here. And again, binary image is roughly 500 and 600. You can see 600 and something, 400 and something. Okay, so you read the image with a certain flag, and then you get these arrays. This is a 3-dimensional array in the case of an RGB image, and if it's a grayscale or a binary image, these are 2-dimensional arrays. But this is just a sample of an image that is shown in the RGB format. Like you can see that if the B and the R are reversed, because RGB and BGR, the R and B are reversed. If you just reverse it, you get this color. This is more of an inversion operation. Okay, this is just to show you that you need to be careful in interpreting the RGB image, because this is the difference here. We showed I am show, like I am read, I am show is for really showing the image through the matplotlib library, and we use the CV2.cvt color to really transform the color from BGR to RGB, because I am show expects images in RGB format, but CV2 OpenCV uses images in BGR format. We just have to do like a small conversion before we print it. So here we did the conversion to convert from BGR to RGB, and the colors are all right. But here we directly print it without doing that CV2 color conversion, and you get all these like blue and cyan, oranges and apples. Okay, this is just a warning to be careful. So now let's quickly look at some very, very basic operations. Okay. So I'm just going to run this cell, and I'm going to explain. So from now on, let's just compare the images that we see and understand these operations. You can read more about the theory if you're interested, but the gist of it is sufficient at this point. Okay. So the first image we're going to consider is like we're going to convert this bowl of fruits into a grayscale image. You can see here that CVT color is the method that we use to make this color conversion. In a lot of cases, converting it to grayscale and then doing your operations makes sense, because the features are still retained. If you're using some shape detection features and all that, like the color really does not matter. It's the contrast between the objects really that matters. So you can see here that color BGR to gray is done, and it's something. So the first operation we're going to look at is called the basic thresholding. Thresholding, does it ring a bell? We just apply a threshold. We saw that these values can range, once it's grayscale, the values, it just has 2 dimensions, and the values can range from 0 to 255. And thresholding is basically fixing a certain threshold value, and then anything beyond that value is a 1, and anything below that value is a 0. So it's basically like coloring it with black and white. So this is the basic thresholding to convert a grayscale image into binary. And the threshold that we apply here is 127. So this is the image, the grayscale image that we consider, and we threshold that with 127. And the maximum value that's permissible is 255, as we know. And we want to do a threshold, binary threshold. It means anything above 127 is a 1 or a 255. Anything below 127 is a 0. And this inverse thresholding is the other way around. Anything above is a 0, and anything below is a 255. And you can see the basic thresholding really recovers some kind of like a silhouette of the image. And then second one is adaptive thresholding. Here you have to fix the value 127, but here you just use the algorithm to figure out the threshold by itself, depending on its local neighborhood. That's called the adaptive Gaussian threshold. Like I'm not going to get into the specifics of the algorithm, but this is just a way of adaptively thresholding it. And then there's one more algorithm called the OTSU algorithm, which is another way of thresholding. You can see here it's more smooth. Yeah, it's time, of course, So I'm just gonna wrap up in just 2 minutes by going over the main ideas that I had for today. But I am happy to continue it next week. So these are the different color spaces which we use using these color transformations, the CVT color method, and you can see the like X-ray fruits and all that. And then there's this resize operation where like sometimes you need to resize your image and convert them to different sizes. Sometimes you need to standardize your images by converting all of them into same sizes. Use the method cv2.resize by specifying the width and the height. And in doing so, you might really lose some information when you shrink them. You might really need more information when you expand them. So we use some scheme called interpolation to really fill in the blanks or like really smoothen them out. So that there are like these are flags to really specify what is the interpretation. Okay, and then like flipping and rotate these, you can play with this. You can run this cell and you can play with this and see like flipping and rotating images. You can like fix an angle and interact, and you can see the angle is rotated. So these are some like transforms you can do on the images, and you can crop the image by selecting the specific range for cropping. You can see the original image has been cropped to show this tank. And you can do some arithmetic operations here to really like change the images. You can divide, add by some number, each pixel by some number, subtract, multiply, divide, and all these. And similarly, some logical operations to apply a mask and process the images this way. Okay, this is R and this is not to really invert the image and convert it into a negative. Okay, the image can be considered to be like a histogram of values, and you can really change the apply some transforms on the image pixel values to really change the distribution of it. Here it means that there are like pixels in all these ranges 0 to 255. They're distributed across, but after we apply a log transform, like a log function, most pixels are closer to 255. So this might be useful in certain pre-processing applications. Yeah, we will see the rest of them next week, but this is just to give you an idea of applying a filter operation and transformations. So yeah, I think it's time already and people are tired. So we will continue next week. But I hope the basic ideas, you can play with this notebook. The basic ideas are clear. I just wanted to show you some edge detection and detecting some geometric shapes, detecting points and lines. You can go through the code and maybe next week we can continue the discussion. Okay.
Awesome. Thank you so much, Pravish.